What about the load side?
It's the same way, sir.
That's basically the same thing. But here we can really use this formula to help us out. What did I say about the Zener branch? It remains relatively what?
Constant.
This R3, it's a small resistor too. It's like 120 ohms. It can handle a significant amount of current. But again, the Zener voltage is going to remain relatively constant over a what range of currents? A wide range of currents. It's how a Zener works. So we can effectively say, since the formula V out equals VCR 1 plus forward voltage, isn't that? Isn't it that?
Yes, sir.
What's common in parallel?
Voltage.
See? Everybody understand? Are we getting it?
Yes, sir.
Hackman!
Sir.
Are you getting it?
Yes, sir.
All right. Load. That's where we're at now. Increases. Well, we can come over here in this Zener branch. Can I do an arrow point to the right?
Yes, sir.
Relatively constant. Hey, we can do that. If the load resistance increases, immediately think about that branch current. What's it going to do? Does that make sense?
Yes, sir.
Can I do this?
Yes.
So if that branch decreases, that's relatively constant. What the current in this branch, where does that current that's not needed by the decreased load go? It's got to go be felt elsewhere in the circuit. It doesn't disappear. So that must mean, hello, does that make sense?
Yes, sir.
So therefore, I can come to my arrow analysis. Hey, load current decrease. Oh, we're doing a load increase. Transistor, oh, it's going to receive that extra current that's not needed by the load. So I can do like this, can't I?
Yes, sir.
Yeah, what's VR4 going to do?
Increase, sir.
Yeah, there's more branch current. VCE,
Decrease, sir.
because if VR4 goes up, VCE naturally, to equal that 3.6, nearly constant, it's got to do what?
Decrease, sir.
Amazing. Load decreases. It's opposite. If I put a smaller load in here, smaller load, not much, it's less opposition to current, right?
Yes, sir.
So naturally, where's the extra electrons that's like floating around? Hey, let's go over here. Now what's going to happen?
Yes, sir.
So isn't the load the load current going to increase
Yes, sir.
due to a decrease in load resistance? Yes. Guess what we can do now? Oh, well, if it goes up, what does the branch current here have to do? Hey, guess what? Now we're dealing with Kirchhoff's current law, aren't we?
Yes,
Sir.
Hello? Total current has to stay the same, doesn't it?
Yes,
Sir.
So now there's where the compensation takes place when the load changes. Less transistor current. Hey, you can come over here, conduct less. Voltage drop R4.
Decreases.
Since VR4 that goes down, VCE has to. So I need that 3.6 volts back. Amazing. There it is. Now, since day 3 or 4, whenever we started doing the regulators, from that day to now, does this stuff make a hell of a lot more sense?
Yes, sir.
Now, you might not be able to go through the rigmarole that I do to explain all this stuff, but if you have at least yeah, I get it. It's the voltages here, it's the branch currents here, is where the compensation takes place. If you got that, you're going to be okay. If you're not down with theory, guess what?
Screwed.
Well, maybe. Know the arrow analysis, but I just explained, and this time we got a tape to prove it. I just explained both of these in its entirety, the best that I can, as easy as I can, to help you and make you understand. That's how these things work. And don't forget, you guys did the labs, hopefully. I know you did. Well, I don't know if you did them right. Because some of you like to, But what do I always say? If you don't understand what's going on in the lab, raise your hand or come over here. How we doing?
Good.